Section 3.3, Part 1, we finally get to look at the graphical solution to these linear programming problems. You've learned how to formulate them, but now we need a little bit of theory to help us solve them in order to maximize that or minimize the objective function. So what I have here is a typical maximization problem. And I know it's a maximization problem because you can't exceed these in terms of producing. In general, those maximization problems will be bounded regions, whereas the minimization problems will be unbounded regions. So that's kind of how at a glance we know it's a maximization problem. So the region itself is this region sitting in here. So what I'm going to do is take off the rest of the graph just to make the explanation a little bit easier to tackle. So we have this quadrilateral, a four-sided figure sitting in here. We can definitely see that it has some corners or vertices. So the way we're going to talk about are some isoprofit lines. An isoprofit line is a line where the profit is a constant along its whole length. So in other words, any line I draw that's parallel to one of these other lines would be an isoprofit line. So there's one sitting here, there's another one sitting here, and every point along that line would have the same profit in your objective function. We can also draw isoprofit lines that are parallel to the other constraint, and every single one of those would have the same profit in that maximization problem. So those are isoprofit lines. Well, it just so happens we have a theory, and this is theorem 1 in your textbook, that basically says if a linear programming problem has a solution, then it must occur at a corner point of the feasible set. Okay, so the shaded region is what we call the feasible set. And the optimum solution will occur at a corner point of that feasible set of the feasible set. So what we need to do once we've graphed our inequalities, those linear constraints, is come back in and identify the corners. Once we have those corners, no matter how many there are, we're going to plug them into the objective function. And once we do that, one of those corners will yield us a maximum profit or a minimum cost. The theorem does go on to say that if the objective function is optimized at two adjacent vertices, so for instance, if A and B both gave us the objective maximizing or minimizing, but the same answer, then it's optimized at every point on that line segment, because this is an isoprofit line. If A and B have the same output to the objective function, then every point along that line would be part of that profit or would be the same profit. So that doesn't happen very often, but there would be infinitely many solutions. So what we're going to do is kind of ease into it and walk through one example. The book does go into a lot more theory. If you're curious at all, and it should spark somebody's interest, you can definitely read the textbooks sections in terms of why that feasible set is so important. But what we want to do is we're going to come in and our objective, this is example 1. Our objective function is to maximize the profit. And the profit's equal to 4x plus 7y. And that is subject to, so here are our linear constraints. We want 2x plus y less than or equal to 16. We also have 2x plus 3y is less than or equal to 24. I also have y is less than or equal to 7. And then finally, x and y are both positive. So this is exactly where we left off in the other section, and now we're going to pick it up. We're going to graph these, so that's our first step. To help me graph them, I'm going to do some labeling here. So this will be line 1, this will be line 2. This is line 3, so I've got them all labeled. We need those intercepts. So when we find our intercepts, the intercept here would be 8, 0 and 0, 16. Let's see, 12, 0 and 0, 8. And then this one's a horizontal line. And the reason I tend to do this first is it gives me an idea how big I need to make my axes in order to graph them. So I need to go up at least to 16, or in this case 20, on the y-axis. Okay, so line 1 cuts through on the x-axis at 8 and on the y-axis at 16. Boy, I really, really hope your lines are straighter than my lines. Very hard to get a straight line on the board, but again, that's why a nice ruler would help. Okay, that's better. Let's test it. So if we plug in the origin, is 0 less than or equal to 16? That is true. So I know this is going to shade towards the origin. For the next one, it cuts through on the x-axis at 12 and on the y-axis at 8, 5, 6, 7, 8. That was a little straighter. If we test this one again using the origin, 0 is less than or equal to 24 is a true statement, so it also shades towards the origin. We also have y is less than or equal to 7. So this was at 8, this is at 7. It's a horizontal line, and smaller than 7 would point down. So here is line 1, here is line 2, and here is line 3. So we've got them graphed. We also know because of x and y being positive that we're in the first quadrant, so we'll tack those guys on. So I tend to not label those. We automatically are restricted to that first quadrant. We need our region. So for our picture, our region is this 5-sided shape sitting here. 5-sided shape is a pentagon, but it's not a regular pentagon. So there's our region. You'll notice that what we did on in section 3.1 is a tiny part of the overall picture. Let's come in and label the corners. So we know that in order for us to have a maximum, it's going to occur at one of the corners. So I usually start at the origin myself, and then I go counterclockwise for some reason. So there's point A, here's point B sitting here, here's point C, here's point D, and down here is point E. Now A we know is at the origin, that was easy. B we also know because it's an intercept, it's at 7, so it's at 0, 7. So kind of tight to squeeze it in there, 0, 7. E we also know was at 8, 0. So the only ones we have to figure out is where C and D are. Well, you know how to solve the system of equations. We did that in the last chapter. So let's go see if we can find point C. So point C is where the horizontal line, which is y equal to 7, and line 2, which is 2x plus 3y is equal to 24. And that's why we were very careful about labeling and bookkeeping. Well, we just need to solve this. We can plug in a 7 right here. So 2x plus 3 times 7 equals 24. That's 21. So 2x is equal to 3, and x is 1.5. 3.5, 3 halves would also work. Okay, so we now know where that point is. So point C, this is where I really wish I had a bigger board. So point C is at a y value of 1.5 and an x value of 1.5 and a y value of 7. Now we need to go find point D. D, and I'm just looking, 1.5 looks about right. Line 2, yep, making sure everything is correct at this point before we move on. Okay, so point D is where line 1 and 2 are intersecting. So let's let's copy 1 the way it is. That's 2x plus y is less than or equals 16. I'm going to do a -1 times equation 2. That'll make my x's cancel. So this -2x minus 3y equals a -24. Adding those together, I get -2y equals a -8, and y is equal to 4. So not too bad on my picture. And then I need x, so I just plug that back in. So 2x plus 4 equals 16, 2x equals 12, and x equals 6. So D is at the point 6, comma 4. So I've now found all 5 corner points. I tend to organize my work again in a chart just to help me out. So here are the corner. And then here's the profit. And here's P, which is right there, 4x plus 7y. Okay, so A, which was at the point 0, comma 0. We have B, which is at the point 0, comma 7. We have corner C, which is at 1.5, also 7. We have D, which we just found at 6, comma 4. And then finally we have E, which is at 8, comma 0. We're going to plug each one of those sets of x and y coordinates into the profit function. So when we have no a and no b, sorry, no x and no y, the profit is 0. Here it would be 4 times 0 plus 7 times 7, which is going to give me 49, usually in dollars. Down here we'll have 4 times 1.5 plus 7 times 7. So you can automatically see how this one's going to be bigger than this one. So 4 times 1.5 would be 6 plus 49. 6 and 49 is 55. Down here for D, we'll have 4 times 6 plus 7 times 4. So that'd be 28 and 24, which is 52. Let's make sure 28 and 24, 52. And then down here, we're going to have 4 times 8 plus 7 times 0, which is 32. So for us, sitting right in here is our maximum. So provided we've done all our arithmetic correctly, our maximum profit occurs at the point 1.5, comma 7. And profit of, I like to put the amount in there, 55. And I'm going to assume that it's a profit, it's in dollars. So there's your first one.